Okay, so for the second lecture, I will continue with kind of basic concepts. Yesterday we saw some basic concepts of information theory, and now we will go to some basic, well, basic but not so, some of those concepts, especially non-equilibrium free energy, has been introduced in the last 10 years or so. So it's basic stuff, but not, but kind of recent. So the third section of the course is this something about thermodynamics. So we will talk about heat, work, and free energy, and the extension of free energy to non-equilibrium systems. This is what I will explain now. So we will focus mainly on systems in contact with a single thermal reservoir at temperature T. So the setup that I'm going to discuss today and tomorrow is a system in contact with a thermal bath at temperature T, single thermal bath, and also operated by some agent. This is the Szilard, what we saw yesterday. No, the Szilard engine is one example, is all the time is in contact with the thermal bath at a given temperature, and there is a demon or agent that changes, introduces the piston and so on. In general, this will be like changing the Hamiltonian of a system. So we have the external agent, which modifies some parameter lambda. So my Hamiltonian is going to be h of x lambda. Lambda is a parameter, and x, I will use x for the microstate of the system, so it contains all the information about the system, the velocities and positions of particles and so on. So this is going to be my microstate, and my external agent is going to change lambda and modify lambda along a process which has a duration from 0 to tau. So this is the setup. So this includes many thermodynamic processes like cycles and things like that. And we are interested into heat and work are just energy transfer between my system and the surroundings. Q is the energy that the system exchanges with the thermal bath, and we will consider positive Q when all the energies are positive when entering into the system. And work is going to be the energy introduced by the external agent. And there is the way to distinguish between the two is to calculate the variation of the energy along a process. And this variation of energy has two parts. One is because of the change of lambda. So one is going to be, if I have some, this is the state of the state at time t, probabilistic state, no. So this gives me the probability to well, let me, this is the derivative with respect to time of this thing. And this is going to be the state. And this is an integral over all my microstates, or a sum, or if you like. I think I've used sums well, it's the same, it's some, or depending on if x is continuous or discrete. And then you have two terms here. One is this one, the derivative of the Hamiltonian with respect to lambda. And here I can put lambda dot. And this is going to be the work. And the rest which is the change of energy due to some relaxation of my system, or some the evolution of my system. This is going to be the, sorry, this is the x here. And this is the heat. I don't know if you are familiar with this, but it is just to split the energy change into these two parts, the heat and the work. And the work, as you see, the work can be written as this is the mean value, no? This is the mean value of the derivative of h with respect to lambda times lambda, and lambda, yeah, times lambda dot. And this is what we call a force, thermodynamic force is the derivative. Actually, what is inside the average is a mechanical force, but when you average it, we call it a thermodynamic force. And this is the work and heat for this type of systems. You have an exercise. The exercise number 3 is to play with these definitions in a very simple system, a harmonic oscillator, and also for quasistatic processes, it's very easy when you have that probability of finding my system in a state x is given by the thermal state for the instantaneous values of my parameter. So this means that in a quasistatic process, my system is in equilibrium all the time, in thermal equilibrium all the time. So instantaneously is in equilibrium, and this is true if lambda dot is small. Then for these processes, you can prove that this is the derivative of the free energy. This is the derivative of the free energy, where this is minus kT, the log of the partition function. And then when you have this, the work becomes, in this case, is an exact differential. So the work is just the derivative of the free energy with respect to lambda times lambda dot. So this is an exact differential that you can integrate along the process. You have that the total work, which is just the integral between the initial parameter and the final parameter of this thing. Sorry, because it's an exact differential, this is just, you put here this, and then you find that this is the equilibrium free energy at the end minus the equilibrium free energy at the beginning. So this is that just in reverse. This is quasi-static reversible process. Work is equal to the delta free energy. For arbitrary processes, we have that this is positive. That you have to do delta F is the smallest amount of work that you have to do to go from one state to do some process. This is This is actually the entropy production. And this is bigger than 0. And it's equal to 0 only for reversible processes. So this is a reminder, I mean, a brief summary of basic processes, statistical physics of processes and thermodynamics of processes. Okay? Questions? Yeah? Huh?
When we say lambda dot is small, it is small compared to...
Yeah, good question. Is it small compared? This is why I didn't put small. Than it's much smaller than the relaxation time of the system. So when I didn't say anything about this px of t, but px of t can be obtained depending on the system. Can be the evolution of this object can be governed by different equations depending on the system. For instance, for a Brownian particle, this will be a Fokker-Plan equation. For if I have a chemical system and x is discrete, or quantum mechanical system with x discrete, and I have jumps between the systems, this could be a master equation or Pauli equation. And we can have even, for an isolated system, this could be a Liouville equation as well, or Heisenberg equation in the case of quantum mechanics. So you can have different possibilities for that. And in all these possibilities, the P of x, the state, the probabilistic state changes. And usually, and not in the last two, but here you always have, the stationary state is this one. So when t goes to infinity, this goes to this, let's call this equilibrium state. And it relaxes to this equilibrium state for a fixed lambda, and this relaxation has a typical relaxation time, which is normally the first eigenvalue of the equation, the first non-zero eigenvalue of the equation, and this characteristic time is the one that tells you if this when the process is quasi-static or not. Okay. Questions? No. Okay, so let's go to the. We want to go beyond, especially beyond this equation, and also we want to compute heat and work for processes which are not quasi-static, and also for processes in which we start in non-equilibrium states. So, and this for those. We have the non-equilibrium free energy, which tell us how the energetics of the system is going to be. And the free energy of a system, the free energy is the energy minus temperature times entropy. And the non-equilibrium free energy is defined like, I will use this notation to distinguish from the equilibrium free energy. And I will also make explicit that it depends on two things, on the state of my system, rho. Sorry that sometimes I use rho and p, but let me use rho for now. And the Hamiltonian of my system. And it's defined as follows. This is energy minus time and the Shannon entropy. So remember, H rho is going to be, I will have some parameter lambda probably, and rho x. And Shannon entropy is minus k rho log rho. This is the non-equilibrium free energy, which was introduced in the. There are some books that introduced in the 80s this quantity, but it was really used extensively in the last 5 or 6 or well, 5 years, I would say. Let me explain some properties of this object. First, when the system is in equilibrium, so if remember, rho equilibrium is this thing, this state. If a system is in equilibrium, then the non-equilibrium free energy coincides, because the entropy coincides with the thermodynamic entropy, coincides with my equilibrium free energy. And this is, remember, this is minus kT. So this is the first property. The second property that you can prove is not hard to prove mathematically is that the non-equilibrium free energy is related with the equilibrium free energy in this way. Is the equilibrium free energy plus some extra term due to the non-equilibrium nature of my system, and this extra term is just the Kullback-Leibler divergence between my rho, my state, and the equilibrium state. So, and this means that the non-equilibrium free energy is always bigger than the equilibrium one. And it's only equal to the equilibrium one if the system is in equilibrium. This is actually what Suri showed you this morning of the when he showed this formula of the dissipation, the entropy production of a polymer that it's trying to copy a template. It's precisely this. In this case, in that case, he showed that the polymer, the difference between the polymer and the equilibrium polymer, let's say, is contributing to the entropy production. Sorry?
Like, this is not like non-equilibrium, and like there are two temperatures, not like that.
No. Here, the equilibrium free energy is only useful, I would say, for systems that are in contact with a thermal bath with a given temperature. So the temperature must be, well, you can of course define this for anything, but it's useful in the case where you have processes of a system in contact with a thermal bath, but the process, because of evolution or whatever, not necessarily is in equilibrium with the bath, but it's in contact with the bath. And this is why this T, the temperature T, is the temperature of the bath. Although the system doesn't have a temperature, maybe, because, well, we don't know what is the temperature for a non-equilibrium state in general. So T is the temperature of the bath, yeah. Okay, this is so far a definition, but when the definition becomes important is when we derive this property, and it's the following. If I want to drive a system from a state rho to a state rho prime, and I want to do this isothermally in contact with this thermal bath, and using some protocol, moving my lambda, my parameter lambda in some way, then the work that I have to do is always bigger than the difference of free energies. It's the same as in equilibrium thermodynamics, but now I'm talking about how to connect systems which are in non-equilibrium. So this is rho prime. Of course, maybe I have to change as well the Hamiltonian, and then this is equal to h, the increment of free energy. We will call this delta F. And this is the basic property that we are going to use to derive all kind of things for information systems for thermodynamics of information. The general proof of this, you can find it in the paper by Esposito and Van den Broek. But there is a very simple proof for a special case, which is the case, suppose that I have a potential like that. So this is my Hamiltonian, let's say, and I have a non-equilibrium state. This is my rho. And if I let the system relax to equilibrium, so this will be a spontaneous relaxation. And my system now will be like that. No, this is V. Let me call this V0 and this rho. So I will have V0 and I will have equilibrium, the equilibrium state rho 0x. And the process is irreversible, so there is an entropy production. And if I want to go back to my system again, I have to do some work to go back to the original state. But I can go from rho to rho 0 in a completely reversible way. Reversible in the sense, operationally reversible, in the sense that I can invert my system and I recover all the work that I've invested. And the trick is the following. If you, instead of let the system relax, you immediately, at time 0, you change your potential in such a way that your system is in equilibrium. So you do a rapid or a quench of the potential. So rho is like that, doesn't change. This is my rho. But now you change the potential in such a way that how we should do something like that, no? So you change the potential in such a way that the system is in equilibrium, and then from here you move that to there quasi-statically. You can do this process, and when you do that, you can calculate the work. Actually, it's not hard to calculate the work. You have a work in the quench plus a work in the quasi-static. The work in the quench is very easy to calculate because it's, well, let me call this Hamiltonian, although it's the same. You can think of a profile of energy. And then here you have, when you do this abrupt change, the energy that you put is precisely the energy at the end minus the energy at the beginning. Sorry. Here there is no heat. All the change in energy when you change the potential is energy that you put into the system because it's instantaneous and the system doesn't have time to relax or to exchange energy with the thermal bath. It's the only energy that you put. And when you go from here to here, you can apply normal thermodynamics because here everything is equilibrium. And then you have the work to do to perform this process is just the difference of free energies. So I have the free energy of the final one, which is energy minus Ts minus the free energy of this one. And you see that here this cancels, and I get precisely the free energy of the last one, which is this one. Minus, and this is non-equilibrium. This is non-equilibrium stuff. And I have the free energy of the initial setup. So you see that in this process, the work that I perform is the difference of free energies, and also is operationally irreversible. You think if I'm here, I can go quasi-statically here, and I recover all the work that I put, and then I quench this to this state, and I recover all the work that I put. So it's operationally irreversible, and the work is given by this difference. So here you have this inequality that we have shown before, that the work must be bigger than delta F. Here is an equality because it's reversible. Actually, we can define a entropy production, which is just the excess of the work that we have done divided by the temperature. This is an entropy production. Okay, so do I have? I have 1 hour, no? Okay. This is the central result that that work is bigger than the free energy, that the free energy change. But you can, and I think this is a very nice result, but you can argue, and actually I would agree with you that in which situations we can really use this result, because here we have to make a fast quench in equilibrium, but I mean fast quench from the non-equilibrium situation to an equilibrium situation. But this type of non-equilibrium states are always relaxing. I mean, apparently it's not, if I have a non-equilibrium state, it will be relaxing all the time. So one can ask if this type of process or this type of inequality is going to be useful at all. Because first, this is very unstable in the sense that this situation is going to be relaxing all the time. So this is, as I said, I agree with this objection or with this criticism to the non-equilibrium free energy, except if I have systems which are non-equilibrium states, but stable or metastable, or if you like, with some relaxation time which is very large even. And when do we have this type of things? So the example is a system with a big barrier. Suppose that this is my potential or my Hamiltonian, and this is a big barrier, much bigger than KT. And I have a state which can be in equilibrium, in local equilibrium in each well, like this. But this is clearly out of equilibrium, because equilibrium, the thermal state should have much more population here than here, because this has less energy. This is a non-equilibrium state. But it doesn't relax. It is very robust. And one of the main ideas of the course, or the things that I want to convince you, is that information devices are like that. Information devices are systems where that can, a memory, for instance, is 0, 1, and it can be 0 or it can be 1 independently of the conditions, no? At least for a large range of temperature. And it can be in any combination of, if you put this, if you consider this 0 and 1, a memory can flip between 0 and 1, but is essentially stable, even though it's at a finite temperature, it's stable. You let it in 0 and it's 0, and you let it in 1 and it will remain in 1 all the time. So informational states or information devices are devices where you have this coexistence of states and coexistence of metastable states, and you can arrange these states out of equilibrium, like this one, but locally in equilibrium. And these states are stable. They don't relax, they don't move. And then I can apply all this setup to those states. And then I can ask what is the probability to go from one of these non-equilibrium states to another equilibrium state. So this is the main idea. The main idea is to define informational states. I have a device or a memory with a lot of states and a possible Hamiltonian or potential. And I have my 1, 2, 3, I can label my states. And then my system is going to be in equilibrium locally. So rho of x is going to be exponential of minus beta h divided by zeta when the state belongs to one of these regions. Let's call this region Rm. But the probability to be in one of these regions, Pm, is going to be Pm. This is not necessarily in equilibrium. So my informational states are going to be defined by Pm. And actually the equilibrium Pm, one can show that it's Zm divided by Z, where Zm is this integral, an integral over the region M of the exponential of minus beta h. But I can imagine other states like this one, where they are not necessarily in equilibrium. Then I can ask what is the work to drive the system from informational state to another one. And this would be given by the delta of f, or if you like, f of Pm. And I can assume here the same Hamiltonian. And this is the equation that explains most of the thermodynamics of information devices. So if I have, because it tells me changing from Pm to P prime M is information processing. For instance, Landauer's eraser is just going from Pm 1/2 to Pm equal 1, 0. or any other information processing that you can imagine is given by this transformation. And this equation tells you what is the minimum work that you have to perform to perform this transformation. So this is the basic stuff. Moreover, for informational states, one can prove that, and this is also, all these proofs are very easy to do, so you can do it by yourself, is this is the sum of the equilibrium free energies. This is minus kT log Zm. So this is like a physical free energy that the memory has, because it's in some, it's like the free energy of each of these wells here. But there is an extra term which is the Shannon entropy of the memory. This is the Shannon entropy of the memory. So you will see that the free energy, if I have a very disordered memory, this decreases the free energy and decreases the ability to make work or makes because this is if I have a a state with a very high energy, then I can go to this state and extract work. Sorry, no. If I have a very high energy, free energy state, and I go to a lower free energy state, I extract work. So I can extract work. This equation is telling me that if I have a memory which is very well ordered, I can extract work from this memory. Also, there is there is an equation based on the Kullback-Leibler divergence, and it's telling you, sorry, there is a KT here. This equation is telling you that the system, if the memory is out of equilibrium, I also have high free energy, and whenever I have a high free energy, it's like in thermodynamics, I can extract work from that memory. So I can extract work from a memory if the memory is very far from equilibrium, or as well, I can extract energy if H is very low. By increasing H, because there is a minus sign here, by increasing the disorder in a memory, I can extract work. This is actually called information reservoirs, and there are nice papers by Chris Janciski and Udo Seifert on the possibility of extract work from an ordered memory, like a memory with all zeros, for instance. In a memory with all zeros, by disordering these bits, you can extract work. Okay, so any question with free energy? This is essential. What we are going to do in the following is just application of this formula that I highlighted there. How do we go from one distribution to other? That's by changing the lambda. Yeah, by changing the lambda in a process by changing. Lambda, the system will always be for a given lambda. For a given lambda, if you fix lambda, we are always talking about systems which are in contact with a single thermal bath and with an agent that moves the Hamiltonian. So if the agent decides to stop the protocol and lambda is fixed, then the system relaxes to equilibrium. But well, your question is, of course, if I'm in this situation, the relaxation will take the age of the universe to relax. I mean, this state will relax eventually to equilibrium. Equilibrium will be like that, no? So I need my probability to flow from here to here, and this will take the age of the universe if the barrier is 20 times kT, this will be impossible. This happens in high barriers and also in phase transitions. When you have we talked yesterday about the easy model, and when you have the easy model also breaks ergodicity, and then it takes, if the system is large, it takes the age of the universe to flip the whole Ising model from minus to plus. Sorry? Are pseudo stationary states. So if you if you write the Fokker-Plan equation, for instance, suppose that this is a continuous variable, it's a Langevin equation. If you write the Fokker-Plan equation, mathematically, the Fokker-Plan equation has a unique stationary state, which is the equilibrium state. But the second eigenvalue, it's so small that the relaxation time is completely, it's almost infinity, if you like. The relaxation time is of order, the relaxation time of this is the order of the Kramer's times, no? It's delta E kt plus here some the omega of this. So it takes very, so you can consider, but it's not mathematically, it's not stationary. It's what we would call metastable, if you like. But if you think of information devices, even in nature, they are like that. You need some robustness of your informational states. So what happens in DNA? DNA is like that. Is you have your DNA is CAT, whatever sequence, and this any sequence is equally probable, if you like. If you assemble DNA from bases, no, but once you form one, this is stable in this sense. And a memory, a hard drive is also like that. So you need always this robustness of states that is a kind of symmetry breaking, because the memory can be 0, 1. This specific basis of DNA can be C, A, G, or T, and it chooses one. This is the idea of these states as well, no? Usually this will be a delta of m something, because it will be one single state. But with this equation, we have an idea of what is the relationship between the information and the thermodynamics. Sorry that I use H for the Hamiltonian, and this is H for the Shannon, but I guess you will not confuse each other. Questions? So, just last property of the last property that I want to show you of the free energy, non-equilibrium free energy, is that if I have X and Y are the microstates of two systems, and I will assume that the systems are non-interacting, so there are no, the Hamiltonian is just the Hamiltonian of one system plus the Hamiltonian of the other system, that they could be correlated. This would be the case of measurements. For instance, when you measure something, at least in classical physics, you interact, your measurement device gets correlated with your system, but they are, after the measurement, they don't interact anymore. So you can have correlations between the two. In this case, the non-equilibrium free energy well, because there is no interaction between the two. You have the energy is additive, and remember that here I have to put the entropy, but for the entropy, I recall you what we defined yesterday, the mutual information. And the mutual information, the entropy of a compound system is the entropy of each of the systems plus the mutual information, or minus the mutual information, sorry. Remember this formula that we wrote yesterday? The formula is that HXI is HX plus HY minus the mutual information. We said yesterday the bits that I need to describe two variables, it's a smaller, when I don't take into account correlations, this is the number of bits that I need to describe X and Y. And this is what I save when I take into account correlation. So if you plug this here, then you get the entropy, sorry for the confusion between H in the Hamiltonian and the Shannon entropy, but you get here the free energies. So here you get the free energies of X and the free energy of Y. And here you get KT, the mutual information. So when I have two systems which are correlated, the free energy is the sum of the two free energies plus the mutual information. And you see that the mutual information, which is a measurement, is a measure of correlations, is something that increases the free energy. So correlations increase the ability to extract work. Think of free energy as an ability to extract work. When I have two systems correlated, which is what happens in the Maxwell demon, in the Szilard engine, that the measurement device and the system itself become correlated, then I have more capacity to extract work. So this will be important. The mutual information is a measurement of the work that I can extract due to correlations. The Hamiltonian must be like that. Otherwise, this is not true. Yeah, suppose this is, we will apply this when you, of course, to grow correlations, to create correlations, you need some interaction in the past. Yeah, of course. But you can, the nice thing here is that this allows you to just forget about the dynamics of how the correlations have been created and just look at the final result, and the final result is this free energy. You know what I mean? That this is the nice thing of thermodynamics, that sometimes you kind of forget about the details of the process, what are the Hamiltonians and so on. You have inequalities or equalities sometimes for just the final, everything depends on the final state and the initial state. This is what we are trying to do here as well. But it's true that to create this correlation, in the past, you need okay. So let's move to the fourth point, which is to incorporate now. Now we can incorporate this to the second law. So, and this is now just a corollary of all these things that we have explained before. So So now suppose that I have a system and I measure the system. So from the consequence of my measurement, the consequence of my measurement is that I have more information about the system. So I have an outcome M. This is the outcome, the outcome of the measurement, and I can update my state, my probabilistic state of the system by just making the conditional probability. The conditional probability is rho xm. I can use Bayes' theorem, and this tells me that Because usually what one has in a measurement setup is the probability to obtain m given x. If the measurement is error-free, there is no error in the measurement, this will be just the delta function of m and x, m is a function of x. But you can have here some errors, and your post-measurement state will be given by that. So now we can see what is the effect of measuring in a system, and this is actually not restricted to these informational states. This could be for any system. We can calculate the increment of free energy in the measurement. Which is just the final one. And the final one will be this. We can assume that the Hamiltonian is the same before and after the measurement, so we have some interaction between, as we discussed before, you have some interaction between the system and measurement, but before the measurement and after the measurement, the Hamiltonian is a given one, is h. So this will be the free energy of my system after the measurement, if the outcome is m, and now I can average, because here we can also study specific values for m, but first we are interested in the averages. So we have the average of this. This is the final free energy, and the initial free energy would be this one. And well, using what I did before, and using the fact that the energy is the same, that the measurement doesn't change my energy as well. No, sorry, it can change the energy, because here, when you average the energy over this, and then over PM, is like the energies cancel. And then you have only the Shannon entropy, so you have T Sx minus Xm, and this is the mutual information. What we see here is that the measurement increases the non-equilibrium free energy, or increases our ability to make work. And this is normal, because it decreases the entropy of a system. When I measure, usually this is, somebody told me yesterday, this is not always true, but usually when you measure something, this has less entropy than this one, although for a specific value of m is not true always. But in average, this entropy is always smaller than this one, because you have more information, your uncertainty decreases. So and this means that the free energy increases. But the mutual information gives you the amount of free energy that you get by the measurement. As I said yesterday, in this lecture, I don't care about the cost of measurement or the cost of erasure. Here we are only talking about the effect of measurement on the thermodynamics of my system. And tomorrow we will talk about how to incorporate the daemon or the measurement device in all this picture. But today we are just trying to quantify, if I measure something, how much work can I extract? And this is the answer, actually. If I measure something, I get an extra kTi of free energy, so I can extract this energy. Actually, the second law, if I have a process connecting equilibrium states, if you like, or non-equilibrium. It could be non-equilibrium. But if I have a process and in the middle I have some measurement, so I go from equilibrium to equilibrium, and I have a measurement here, and my measurement correlates my measurement outcome and my system with some mutual information I, then the second law is like this. It tells you that work is bigger than delta F. This is the second law, normal second law, and with information I have to add now KTI. So this is, and you see the mutual information appears in as the quantity that tells you how much free energy your measurement has give you or has produced. For a cycle, delta F is 0, so you have that the work is bigger than minus KTI, and in reversible conditions this is equal, and then we can extract work, because remember that negative work means that we extract work. And the simple example, is the Szilard engine. And in the Szilard engine, you see that I is IXM. Remember that if there is no error, there is the entropy of M. And this is KT log 2. Sorry, this is log 2. So the work we can extract is, well, the work is bigger than minus KT log 2. And the Szilard protocol satisfies, meets the equality. So in the case of, because everything is done reversible, and we can do it reversible. Okay, in the exercise number 2, we will do it this afternoon. You have to repeat this for a Szilard engine with errors. So you have to calculate the mutual information when you have an error. So you measure left, right, but sometimes you get the wrong answer. And then this is smaller than log 2. It could be 0 if your error is, the error is very big. And then you have this, you can extract less work. And I also propose you to design a protocol that extracts that amount of work. This is what you have to do in the exercise, okay? Sorry? I cannot hear. Sorry.
So in the diagram, so for the measurement, I mean, I'm just confused on what the measurement is. Should I think of it as another system which is connected to another bar, or how should I?
Yeah, as I said before, the problem of thermodynamics of information can be split into two things. One is how information enters into the second law, and this is the answer. But we don't care about the physical nature of the measurement device or the physical nature of the measurement process and so on. This will be tomorrow when we will incorporate the measurement device or the demon, if you like, and we will compute the free energy of the demon and so on. But it's good to split the problem into two, because here what we are only interested in what happens if you have feedback. If you have the possibility to measure, how can I, first, how much work can I extract if I measure? This is the answer. The second question is, how can I fulfill this how can I reach the quality here? So how can I build an optimal Maxwell demon from information? All these problems, you can answer these questions without taking into account the physical nature of the measurement and so on. This will be tomorrow, and of course this is more interesting from the point of view of foundations of statistical physics, because what you want is to incorporate the measurement device and recover the original second law and so on. But I split the problem into these two separate, completely separate parts. The energy, well, in the measurement, yeah, the measurement assumes that you have your system and your measurement device. There is a Hamiltonian. Actually, the Hamiltonian is only for the system. You only care the Hamiltonian of the system. And through some process, you don't know which one, you get a correlation between, actually, as a random variable, x doesn't change. This is an ideal measurement. You don't change your system, and your memory gets correlated with the system, and the Hamiltonian doesn't change. So this is why the energy, the energy. I don't know if you can see here. Here you have the energy of this state minus the energy of this state, average over m, and this is equal. They cancel. If you calculate the average of rho x, you can calculate this average, and then this one. These don't cancel, but when you multiply by m and sum, this becomes equal to this, and they cancel. So the energies cancel, and they are only the entropy is only entered into the equation. It's okay. Okay, so we will continue now with trying to solve a second question. The first question is how to incorporate information in the second law, and this is the answer for a measurement. This is the answer. For information reservoirs, you can incorporate the information in the second law in different ways, but for a measurement, this is the answer. And the second question is how can I do a completely how can I meet this equality? So how can I build Maxwell demons which are optimal Maxwell demons? And this is what I'm going to tell you now. So to answer this question, we have first to introduce fluctuation theorems. And then I will finish with with the idea of how to perform this optimal Maxwell demon. So for fluctuation theorems, fluctuation theorems tell us about not only averages over this realization. All these things that we have here are averages, but fluctuation theorems also tell us how the energy transfer, like heat and work, change in a single trajectory, which is usually, because the system is in contact with a thermal bath, is a stochastic trajectory. So We have stochastic values for heat and work, and this is the definition of stochastic, or sometimes they are called trajectory values as well. So, for instance, you can define an energy for or energy change, which would be the derivative of the Hamiltonian. And now x is a stochastic trajectory, so you can have x of t, your stochastic trajectory. And you can define as well work. Well, actually this is lambda, and lambda equal lambda of t. And you can also define heat. Heat is a little bit more difficult, because how can you define heat for a trajectory which is fluctuating? But we have the first law, and the simplest way to define heat for trajectories. Sorry, I don't know why I put this x here. Is just to say that it's all the change in the internal energy that doesn't this is u, sorry, that is not introduced by the external agent. Actually, w, small w there is just mechanical work, because it's force times displacement. And Q is just the rest of energy that doesn't come from the thermal bath. Okay, and also it's possible to define entropy and even a mutual information for trajectories. Using these definitions, Crookes was able to prove the following. If I start in equilibrium and I go to another equilibrium state, moving my parameter, then he proved the following, and you have the proof in my notes here. He proved that the probability to observe a trajectory, this is, I will call gamma the whole trajectory, divided by the probability to observe the inverse trajectory when I invert the process. This is the exponential of beta, the work, minus delta F. Some of you probably have seen the Crookes theorem. In this way. This is equilibrium. But this is more general. This is for trajectories. This is not even, I don't know if everybody's familiar with Crookes theorem and fluctuation theorems. If not, well, this is the result. This is the usual way of expressing the Crookes theorem, but this is more general. And this has been applied many times. This is, for instance, from this theorem. If you take this to, if you take this here, and this to the right-hand side, and integrate over omega, you get that the average of this quantity is equal to 1, which is the Jarzynski equality. And it's the relevance of the Jarzynski equality is that it's the first time that there is an equality for arbitrary non-equilibrium processes. We have a lot of equalities in thermodynamics for equilibrium processes, quasistatic processes. Far from equilibrium, we have only inequalities. We used to have only inequalities. This is the first equality that tells you something about the fluctuations of the work. In this case, this is a stochastic. You see, this is the probability of getting some work. Okay, there is a very nice result by Suri and Jordan Horowitz. The Horowitz, I never know how to pronounce your name. It's a fluctuation theorem for feedback systems. I don't have time to prove it, but let me tell you that as well as we define quantities like work, heat, and energy, we can define a mutual information theory. Mutual information for trajectories. And actually, I will use small letters for this quantity, and this is this depends on a specific trajectory and a specific outcome, and is the log of the probability to have a trajectory and an outcome divided by the probability of having a trajectory and the probability of having the outcome as if they were uncorrelated. And the average of this I is the mutual information between my system and the measurement device. And using this equation, they could extend Crookes' theorem to the following theorem. Yeah, you can find this in is Physical Review E in 2010. Okay, I'm sorry that I cannot really. The notes is my plan was to prove Crookes' theorem and this theorem, but I'm out of time, so I cannot give it to you the proof. But this was important. This had a nice application, which is the one that I want to tell you now, which is how to find the optimal, how to answer the second question, how to find the optimal Maxwell demons once you have some measurement. And it tells you this theorem. Well, you can get a kind of Jarzynski equality and also the second law using this. But it tells you that the most interesting trajectories here are the ones that make this equal to this thing. And these are called reversible trajectories or reversible feedback processes. So in reversible feedback processes is when you have the same probability to observe a trajectory or sequence of states in your process, but when you revert the process, you see the same movie. You have the same, you see the same trajectory but reverse in time. Okay?
M here is measurement?
M, that's a good question because I forgot to tell it, that M is the outcome of your measurement in the forward process. In the backward process, you just choose M at random at the beginning of the process with the same probability distribution that in the backward. So it's a technical detail, but it is a, you take, you have here your measurement at some time. And this gives you 1, 2, 3 M outcomes, no? Possible outcomes with some probabilities. Then when you do the backward process, you have to choose M from the very beginning with this. Okay? So this gives you a kind of recipe to get optimal Maxwell demons. And now I will do it in the last 10 minutes. No, I have 10 minutes. I will do it only for error-free measurements, but it's not hard to do it for error-free measurement, for error.
Did you say only those trajectories are
Those trajectories are the ones that give you the optimal, they give you a work which is equal to the maximum one. This is the maximum work, and these trajectories give you this one. Okay, so the recipe that this formula that you see here is to try to make a forward process and a backward process, and they have to look exactly the same. And actually, if you do it quasi-statically, this will happen all the time. But the critical point is the measurement. So in the measurement, you need that in the measurement, after the measurement, or at the measurement, the two trajectories are exactly the same. In other words, you need that the protocol after measuring an outcome M must be equal, the state after measuring M must be equal than the state when I go back. So if I measure M, I have to run a protocol that when run backwards, prepares the system in a state M. You will see in the examples it's more clear. So here in the Szilard engine is an optimal engine as we have seen before. Here you measure left, right, and what you have to do to extract work from this measurement is the following. It's something that, if reverted, prepares the system into left or right in order to coincide, because the movie in forward and the movie in backward must be the same. So here you have that if you invert this, so you insert the piston and move the piston to the middle, then you get back to the particle in the left container, and this is why this is optimal. The reverse of this step, the reverse of all these things, prepares the system in a state left in this case. Okay, remember this recipe. So if I have some measurement and I want to extract the maximum amount of information from that, the maximum amount of work from that information, I have to do something that when reverted, prepares the system in this state. So this is like lateral thinking. If I want to extract work, I don't have to think of how to extract work. I have to think of how to prepare my system in this state. And then this theorem tells you that then you will extract the maximum amount of work. Let's see the recipe working in some example. This is a paper by Takahiro Sagawa and Ueda in Japan and Kim in Korea. The paper is intended to study the Fermi and Bose statistics of many particle Szilard, but they started with a Szilard engine with two particles. So when you have a Szilard engine with two particles, you insert your piston, and you can have three possibilities. when you have the two particles on the left side, then it's very easy to extract work. And now I'm trying to, I ask you, what can I do to extract work from this situation? And as I said, if you are here, it's very easy. You just expand, as we saw yesterday, and remove the piston and so on. And the same if the two particles are here. But what happens if you get this situation? Then well, you can think, how can I extract work from that? And this is a mess. Well, actually, in the paper, they just gave up and they said, well, we just get rid of this situation. If you compute the work that you extract, the information you get is the Shannon information. This is mutual information because it's error-free. And you have 1, 4, 1, 4, and this is 1, 2, the probability of this situation. So you have 1.5 bits. This is 1.5 bits. And the work you extract, if you do the Szilard idea, the Szilard expansion here, you can calculate it, and it's kt log 2. So you are wasting half a bit, no? Because this is 1.5, and we said that per bit we get kt log 2. And here we have 1.2, 1.5, and we get only kt log 2. So the question is, how can we extract work from this situation? And if you think of how to extract work, you can imagine pistons and things, and myself, I would not be able to do it. But let's apply the recipe. And the recipe is, don't think how to extract energy. Think how to prepare my system in this state. Okay? And this is much easier. If I want to prepare a system with two particles, one in the left and one in the right, well, not so simple. Because, for instance, if the particles are point particles, I tell you, I think it's impossible. And if they are indistinguishable and point particles, I think it's impossible. But for the moment, suppose that they have a finite size. If they have a finite size, then it's very easy, because you can shrink your box. And if you shrink your box, and then you are sure that one is in the left and one is in the right, because if you shrink the box at some height that it's the same size as the particles, and then you can insert the piston and you then expand again the box, and you get this state. Okay, if you do this, you prepare the system in this state, and the theorem tells you this is the optimal protocol, which is non-trivial at all. But if you calculate, if you do now this, shrink, remove piston, and expand, you get work. And you get exactly 0.5. This is actually a simulation where, as a function of the height of the box, and you get exactly the 0.5 bit, the 0.5 kt log 2 that you were wasting, you do it like that. So it's a non-trivial recipe. It's a recipe that you need all these mathematics to and Suri's theorem for getting this. But the final thing has a lot of, I don't know if a lot of application, but it has a real application that it's, okay, I have a measurement, I have a system, I have some information I gather from the system. How can I use this information to extract work? Hal Tasaki proposed that another possibility is, I have many particles and the Szilard. So how can I extract the work from here? By the way, if you look at the energetics of this thing, we had to do the simulations. Well, it's not simulation; it's free energy things, but it's not. It's a little bit surprising that you get work from this, and the reason is that when you shrink, the pressure of two gases with one particle is a little bit smaller than the pressure. So the pressure is nonlinear if the particles have a size. And this is why when they are together, this expansion gives you more work than the work you put here to compress. But this physical thing is, a priori, it was completely unexpected, no? And here, how can you extract energy from this situation? So how can you go back to here and extract energy from this? Again, we don't know. But if you think now, lateral thinking, no? Instead of thinking how to extract work, you think how to prepare. From here, how can I prepare this state? How can I, from here, prepare a state with 3 particles on the left and 1 particle in the right? Well, one possibility is to have traps, like optical traps. For instance, suppose that I have traps. I put 3 traps here, 1 trap here, and then I wait until all particles get trapped. That I need again a finite size, because otherwise 2 particles could be trapped in the same trap. And then I put my piston, and then I remove the traps. Okay? So if you do this, you extract the maximum amount of work again. So it's and actually, here you can calculate the information here is much more, this is a binomial, and you have the Shannon entropy of a binomial and so on. But you calculate the work, and it gives you exactly the information that you gather in this measurement is recovered as work. And also here you can ask, well, why I have, when you do this process, this protocol, you create barriers, you create, traps, you remove the piston and you remove the traps. Creating traps and removing traps looks like reversible. I mean, you have to, you get some work when you create the trap, and you have to put some work when you remove the trap. But turns out that, so it looks like what you gain here, you put it here again, no? But it turns out that, again, when you create a trap and remove a trap, the work you have to do depends on the total volume of your container. So this means that here, creating the trap, when you create the trap, you get more energy than when you remove the trap. And just this coincides with the mutual information, which is amazing. That this is a lot of physics, but here is just not physics. It's just statistics. It's to say that this state is equal to this state, and that's it. There is no. I don't care about if the traps are traps or are. The physical nature of all these things, or the physical nature of this. I could imagine other possible protocols, and as far as they prepare, as from this system I prepare this one with probability 1, then I recover all the information. Okay? So you see that here, answering your question, it's a lot of fun to play without forgetting about all this problem of foundations of statistical physics, that how can we recover the validity of the second law and so on. I prefer to first stay only in the problem of what can I do with information. So my lecture today is what can I do with information. I can extract this amount of work, and how can I do it optimally using this recipe. And tomorrow we will go to this more fundamental problem of how I incorporate the Maxwell demon into my whole system, and then I recover the original second law validity and so on. Okay? So see you this afternoon in the. Thank you.
In previous slide, how shrinking the volume money again, who can extract work?
From this one, you mean?
And when you shrink your
This is because the pressure is nonlinear when the particles, when the gas is non-ideal, the pressure is non-linear in the number of particles. So if this is ideal, then you don't get any work. But if it is not ideal, the pressure here is slightly smaller than here in this situation. This is very nice to write down the equation of state and so on. With the Van der Waals equation, you can do it.